So here we have a Precision Matthews PM-728. Well, kind of. What's that right there? Oh, power feed. Nice. Greetings, fellow DIYer, and welcome to my video. If you own a vertical column mill, you know what a pain it can be to crank that mill head up and down. Good news is there's a solution. Z-axis power feed. There are individuals and companies out there that make kits to convert your Z-axis to power feed. And there's nothing wrong with going that route. But for me, I like to DIY, and I'm also kind of the treadmill guy. So why can't I make something myself and use a treadmill incline motor to do it? First thing I want to talk about is why a treadmill incline motor. Well, the nice thing about these, they have lots of torque. They move nice and slow. If you've parted out any treadmills, you probably got one of these for free, so why not use it? They're extremely easy to wire up, and they're AC. A lot of the kits that I've seen for Z-axis power feed actually use a DC motor and require a DC conversion power supply. In other words, it's a power supply that plugs into 110 AC and then converts it to DC. And I like the idea of just skipping the middleman and going directly with an AC type motor. With my particular mill, a Precision Matthews PM-728, the first thing I had to figure out was how to connect the shaft to the Z-axis lead screw because it's threaded. The Z-axis lead screw is actuated by two conical gears so that you can have a crank on the side that turns the lead screw. The conical gear directly attached to the lead screw is held in place by a 12mm locking nut. Now, the easy way to do this would have been to remove the nut, thread a collar at 12mm, and then either use a Nordlock type locking washer or some Loctite that can be broken away without heat. I didn't really want to do that. I wanted something that I could lock or unlock as I saw fit without damaging the threads. It wouldn't take much to tap a collar at 12mm and then put a set screw in it. But that set screw is going to bind into the threads and damage them. What I came up with as a solution is this little guy right here. This is threaded at 12mm. I can thread this bolt in. We're going to use that in place of the lead screw on the mill. And then this key has been cut with the threads. We can take and fit that into place. And we now have a keyed insert that fits into this connector. With it loose in there, it can slide in and out, and we can loosen or tighten the bolt. We fit it into place, and now I crank down the set screw. I can't get that to budge at all. Basically, that threaded key is acting much like a gib on the teeth of this threaded bolt and holding it in place. If I loosen it up, we can unscrew it, and there is no damage to the teeth on that bolt. I'm really kind of excited about this. This is a really slick way to make a locking fastener that will connect to the threaded end of that lead screw and still be easily removable. Since shooting that first part of the video, I have actually improved on my locking setup. This is the collar that is going to attach to my lead screw. It's skinnier, and that needed to happen to clear the conical gears inside of my mill. Originally, when I built this little piece, I used smaller set screws, and the problem I was having is that the hex inside the set screws was so small that the Allen wrench was so tiny that you couldn't really get it tight. So I ended up drilling and tapping for larger set screws, but that created a problem. So if you look right there, those set screws actually stick out quite a bit, and that created an interference with the conical gears inside the mill. To fix that, what I ended up having to do was drill into my threaded key so that my set screws can fit down inside. Not only does this create the extra room that I need for the set screws, it also helps locate that key. So the fact that I didn't originally plan on doing that, it's actually for the better that I ended up needing to do that. Those are the holes that I drilled, and that helps hold everything in place. I couldn't be happier with how this works. I mean, with one set screw, let's say I tighten this guy down, with just the one set screw tight, there is no loosening of that bolt. So I am very confident that this is not going to loosen up with use. And then when you add the redundancy of a second set screw, that's only going to lock it in tighter and be more stable over the long run. So this is the collar that's going to go inside the mill. Then this is the replacement plate that I created to take the place of the factory plate. Now, it's 1/4 inch, that's probably overkill, but I am going to end up welding some supports to this that are going to position and hold the motor in place. So it was definitely important to make sure that I had a thick, solid piece of steel that could handle the weight. One thing I hadn't originally thought of was the fact that if the shaft goes all the way through and then goes directly into the coupler, and then the coupler goes to the mill head, there's no way to get in and tighten it because this plate would be in the way. So I actually had to break this up into several pieces. This shaft is going to end up sitting like that. Now, it won't be resting on this piece of steel. It'll actually be elevated ever so slightly. Shaft goes there, and then this coupler goes on the top half, and that's what's going to connect to our motor. This is a shaft that I machined to replace the shaft that originally came with this motor. And to do that is really pretty simple. I've had this shaft out. I actually originally turned this down to 5/8. I didn't like the fact that there were still threads exposed when I turned it down to 5/8. So I scrapped that idea, took the measurements. It ended up being too short anyway. Well, that's because I cut it. But then the one that I made is now a replacement. Changing it out is really pretty simple. The first thing we got to do is get into this motor. So once we're into the motor, we can very gently lift up. Now, normally this whole cap would come off. Because of the connectors that I put on the top, they don't currently fit through the hole. So we're just going to set it off to the side. But had I not pre-done those connectors, it would easily pull off. This gear needs to come off so that it is out of the way. And then we have our thrust bearing and a hardened washer. There's one more hardened washer. It is up inside the top plate on this. You have to make sure that's there, otherwise you're going to end up wearing through. This gear is a slight press fit. It's not that tight, just a little bit of pressure, and we can get that up. It's this pin that holds everything together. And on this particular shaft, that pin is a press fit. So we're going to go ahead and knock that out. It's not super tight, so it's not going to take a ton of pressure to get that out. I have a whole other video on disassembling and wiring and all those kind of things for these Treadmill Incline motors. And it's actually a pretty good video. Some of these have stop switches inside. This one did not. It did have a potentiometer to let the treadmill know the height, but I removed that. Had it had stop switches, I would have had to have removed those as well to be able to use it for this application. And just like that, the pin is out. And now we can very gently remove the original shaft. Everything goes back together the same way. The new shaft goes into place. Now, see it right there. I just pushed it off. There is another bearing down in there. And again, we have a hardened washer, so that is all critical that that goes back in the exact same way. You can see that my pin is no longer a press fit, and that's okay. It's not going to cause any problems, because once it's all together, it'll be held into place and located. And we center that up. Put the new gear in place. And that gear is actually what helps hold everything down. Bearing, hardened washer. And now we can put our gear back in place. And that's it. That's all that's involved in changing out to the new shaft. And that brings us to everyone's favorite part of our programming. I just did a bonehead move. I spent all that time telling you how important that it was that the bearing goes between the hardened washers. And what did I do? Watch it right there. I put the bearing directly up against the gear. Thankfully, I caught it in editing. I'm watching the video and sure enough, I didn't put it together correctly. Easy mistake to make, especially when you have stuff reversed because you have two halves. I can't stress enough how important it is to have the bearing between the two hardened washers. The cap back on, fitting it into place. Now you do have to be careful putting these on because there are locator pins that are helping to stabilize those gears. And so everything has to fit back in place. But if we did it right, yeah, when I spin that, I feel tons of resistance, and that's because of the gear reduction. We're spinning this motor pretty fast. And then we'll go ahead and put these screws back in. Now there's actually 6 screws that hold this in place, and I will end up installing the other 4 before I am done with all this. I do want to note that most of these are wired with red, white, and black. White being your AC neutral, red being one direction, and black being the other. But if you look at the 3 wires coming out of this, we've got red, blue, and yellow. So how does that translate? Well, the good news is the wires that originally came out of this unit were correctly colored with red, white, and black. The black became blue inside, the white became yellow inside, and the red was still red. So as you're taking things apart, it's a good idea to note your color combinations. We're definitely getting a whole lot closer, and the next time you see this, I will likely be installing it on my mill. So the very first step in installing that incline motor right up here is to lower the mill head. Now, why are we doing that? Well, this mill head is driven by a lead screw inside the column, and that lead screw is held in place by a conical gear and a nut. And if we remove that nut, the set screws in the conical gear would be all that's holding this head in place. Now, I'm sure you're thinking, well, that's an easy fix. Simply lock the head. And we're going to do that. But do we want to guarantee that all the weight of this head is going to stay put just because we've locked the mechanism on the mill head? I really don't want this to go slamming into the bed of my mill. So I am going to actually cover the bed and then set a block of wood to help hold everything and take the pressure off. This is just a simple piece of plywood that happens to be the right size. And then we have a block of wood. And we are just going to bring this down and take the weight off. Oh, it's a lot of cranking. If only I had power feed. All right, weight's off. We're going to go ahead and lock the column. Everything should be in place. First step in this process is to remove the cover plate from the top of the mill. And that reveals the conical gears and the locking nut. I really don't want to drop this nut down in the column. So very carefully, going to remove everything. Now there's a washer sitting on top of that conical gear, and I am going to leave that there and install my locking adapter. I have this 12mm bolt in the locking adapter as a way to align that threaded key and get everything in the right position prior to threading it onto the lead screw. And that just threads down on nice and easy. All right, we have it nice and tight. I'm gonna rotate this a little bit so that I can get in there and tighten the set screws. So I got the first one tight, but I was having problems getting the Allen wrench down in there because, well, you know, I've got ogre hands. So what I ended up doing was I put it in this pair of vice grips. Now, it's in the vice grips not to create extra leverage. I'm still going to tighten at the Allen wrench, but it does give me the ability to more easily get it into the set screw. All right, both set screws are nice and tight. I think we are good to go. Go ahead and unlock the head. Doesn't seem to be any issues. The set screws are clearing the conical gear. Now the test. See if I can turn this and loosen that. No, it's not going anywhere. So the locking mechanism is working as it's supposed to. The frame is in position. We're going to go ahead and get the mounting screws in place. And I want the shaft to somewhat position this, so I'm just going to give this a little bit of a spin. Make sure everything's spinning true, and it appears to be. So with it spinning true, we're going to go ahead and tighten those down. Coupler into place. I don't want the shaft coupler rubbing on the base plate, so I'm just going to use a couple pieces of cardboard. Just enough to set a gap and get everything located right where I want it. Neoprene piece. Make sure the set screw's tight. This is another good reason that I have covered the bed of the mill. If I end up dropping something or a tool comes down, any of those kind of things, we don't want to damage the bed. All right, the piece de resistance. Now, this incline motor may look a little different than it did on the bench, and that is because I fabricated this fan shroud. I have a computer fan, an AC computer fan here in the back, and the reason I did that is incline motors are not designed to run for extended periods of time. I mean, think about it in a treadmill application. You're going to change the incline and then it's just going to sit there. In most cases, these motors have a duty cycle. It'll say like something to the effect of 1 minute on, 5 minutes off. So this particular motor, under duty cycle, it says internal. And that's because it is thermally regulated. In other words, if it gets to a point where it's too hot, it will not work until it is cooled down. I really didn't want to ever have to be messing with it being too hot. When I ran an incline motor on my DIY mill build, I put a very similar, not as nicely fabricated as this one, but a very similar fan shroud around that motor. And it kept the motor nice and cool. The way this works is I have a master power switch that gets power to this fan and also gets it ready so that I can use the incline motor for my Z-axis. I'll show you that in the controls here in just a minute. Let's go ahead and get this tightened down. Now with it tight, we can go ahead and tighten the set screw on my coupler. And we are all set to go. So this is my control box. It's currently not plugged in. And this is going to fit on top of the mill head. And what I have is a master power. Now this is a lighted switch so that I know when it's on. And what it does is provides power to the fan, and then it also turns on power to this. I didn't like the idea of this momentary switch having power to it all the time. So by having a master kill switch, it makes it so that when it's off, I can hit up and down and it's not going to do anything. Lots of wires to try and route and get into a good position. Now, don't make the mistake that I did. I've made several mistakes on this build, and thankfully none of them were catastrophic. I measured the length of the wires going from my control box up to my motor, not thinking about the fact that the mill head is going to move. And so the two wires that I had, the one going to the incline motor and the one going to the fan here in the back, were too short, and I had to redo them. So my technique for attaching this box to the top of the mill head is really pretty simple. I'm just going to use double-sided adhesive tape. I really like double-sided adhesive tape. It is removable, it's strong, it just gives you lots of options without having to drill into your machine. And then we'll press the box into place. And that is a nice solid mount, and I can route my wires. These wires are going to need a little love. I'm going to have to zip tie the two wires coming from up above together, but for the test, I think we're good to go. Everything's unlocked. Let's raise the mill head up. Now there is definitely a little more resistance than there was before, but not tons. I mean, if I need to crank this by hand, I still have that option. Now that we are clear of our support, let's go ahead and turn that on. The moment we've all been waiting for. That is super nice. That is about the perfect speed. I knew it would be the perfect speed because, well, it's set up to be an incline motor on a treadmill. They don't want it raising so fast that it's bucking the user off, and they don't want it moving so slow that it takes forever to get to the correct incline. Yeah, that is super nice. If you like what you've seen, please click like. If you'd like to see more, please subscribe. Thanks for watching.